Okay, let's continue looking at application of differentiation. In this particular section, we will learn limits at infinity. We use the limits at infinity to find a horizontal asymptote, right? Most of the time. Okay, so objectives, we will learn how to determine finite limits at infinity, and we will see how to determine the horizontal asymptotes, if any, for the graph of a function, and determine infinite limits at infinity. Okay, limits at infinity. So meaning we looking at the two typical case. First case is limit when x approaches negative infinity for function f of x, and also we look at limit when x approaches positive infinity for function f of x. So two typical limits at infinity. Okay, so let's take a look at this function f of x equals 3x squared over x squared plus 1. So this is our function, and we will look at the end behavior of function on an infinite integral, meaning we look at when x approaches negative infinity, what happened to f of x, right? And look at when x approaches positive infinity, what happened to f of x. Okay, if you look at this particular case, when x approaches negative infinity, then f of x approaches 3, and this is horizontal. X equals y equals 3. Okay. Y equals 3. So when x approaches negative infinity and then positive infinity, y value approaches 3, meaning f of x approaches 3. In this particular case, we call this horizontal asymptote. So this dashed line, we call that y equals 3, which is horizontal asymptote. This is a horizontal line. The function gets horizontal asymptote is a horizontal line. The function gets infinitely close but never touch the line, right? Never meets the line. That the function f of x gets infinitely close but never meet the line. Okay. You can also use the table method, meaning construct a table, pick some value from left hand side of the 0 and pick some value from right hand side of the 0. This is left, that's right. And then you look at how does y value changes, and based on the corresponding x values. So as you can see, when x equals 0, then the function y value equals 0. Okay, when x equals negative 1, y value becomes 1.5. When x equals negative 10, y becomes 2.97. When x becomes negative 100, then y value becomes 2.9997. And as you can see, just getting closer and then closer to 3. That means when x approaches negative infinity, y value approaches 3. On the right hand side, right, when x equals 1, we get a y value equals 1.5. X equals 10, y value equals 2.97. X equals 100, y value equals 2.9997. When x approaches infinity, then y value approaches positive 3. Okay. So left hand behavior, right hand behavior actually converges. That means f of x equals 3. That's what we call horizontal asymptote. Okay. The table suggests that the value of f of x approaches 3 as x increases without bound. Similarly, for f of x approaches 3 as x decreases without bound. Then these limits at infinity are denoted by the following, right? Limit when x approaches negative infinity for function f of x equals 3. Limit when x approaches infinity for f of x equals 3. So left hand side limit and the right hand side limit converges. That means horizontal asymptote occurs at f of x equals 3. Okay, so that's basically what we find based on these limits at infinity. To say that the statement is true as x increases without bound, meaning that for some real number m, the statement is true for all x in the interval. Okay, the following definition use this concept. Definition of limits at infinity: that L be a real number, and the statement limit when x approaches positive infinity for function f of x equals L equals a constant, right? L is a constant. Means that for each epsilon is greater than 0, there exists an m, a real number m, which is greater than 0, such that absolute value of f of x minus L is less than epsilon whenever x is greater than m. And the statement limit when x approaches negative infinity for f of x equals L, meaning that for each epsilon is greater than 0, there exists an n is less than 0, the real number m, such that absolute value of f of x minus L is less than epsilon when x is less than capital letter M. So this is actually the definition of limits at infinity. Just basically telling us limit when x approaches positive infinity for function f of x equals to constant L, and limit x approaches negative infinity for function f of x also equals L, then we have horizontal asymptote. Okay. The definition of limit at infinity is shown in figure 3.34. If you look at this graph, as you can see, right, this is our L is right here. So the graph move up and down in a particular boundary, right? Bounded by epsilon. So that's what we call the graph of f lies between the horizontal line given by y equals L plus epsilon and then y equals L minus epsilon. Then it will lead us to a definition of the horizontal asymptote. The line y equals L is called a horizontal asymptote, right? When f approaches the line y equals L as x increases without bound. So just like the other one, the one we just go over, y equals L or f of x equals L. They mean the same thing, right? Indicates horizontal asymptote. Definition of horizontal asymptote: the line y equals L is a horizontal asymptote of of the graph of function f of x, if limit when x approaches negative infinity for function f of x equals to a constant L is constant, or limit when x approaches positive infinity for function f of x equals to L, then y equals L is a horizontal asymptote. In the example of a limit when x approaches infinity for f of x, and then limit for f of x approaches g of x when x approaches infinity both exist, then limit of when x approaches infinity for the combination of the two functions equals to limit when x approaches infinity for function f of x plus limit when x approaches infinity for g of x. So this is sum rule. We also get product rule, right? You can limit of the product equals to the limit for f of x times limit for g of x. And similarly, similar properties hold for limits at a negative infinity. Sum rule and then product rule. If I is a positive rational number and c is any real number, then limit when x approaches infinity for c over x to the r power equal to 0. Meaning constant over infinity, c over infinity equals 0. When x approaches infinity, replace x with infinity, then you know that is c over infinity. Any number over infinity will be 0, so limit is 0. Further on, if x approaches negative infinity for c over x to the rth power also equals 0, because limit when x approaches negative infinity, so we get a c over negative infinity to rth power. We're still infinity, right? So c over some kind of infinity, that also equals 0. Okay, this is very straightforward. If you just direct substituting x with positive or negative infinity. Okay, let's take a look at this particular limit. So we got a limit when limit for when x approaches infinity for function parenthesis 5 minus 2 over x squared. So you can just use this sum rule, right? Separate them into two limit. X approaches infinity for 5 minus limit x approaches infinity for 2 over x squared. Over x squared. Limit for a constant is a constant, and for limit, direct substituting x with infinity, 2 over infinity squared is 5 minus 2 over infinity will become 0, so it becomes 5 minus 0, which is just 5. Okay, so limit for this particular function 5 minus x 2 over x squared is 5. And if you look at the second question, we got limit x approaches positive infinity for 2x minus 1 over x plus 1. And if you do direct substitution, it probably doesn't help too much. So what we can do is divide both the numerator and denominator by x. Okay, now I'm going to divide into both terms inside the parentheses on the numerator separately. So 2x over x becomes 2, and negative 1 over x becomes negative 1 over x. And denominator x over x becomes 1 plus 1 over x. Now we can do a direct substitution. Okay. 2, 1 over infinity, denominator 1 plus 1 over infinity. And any number divided by infinity will become 0. So on the numerator it becomes 2 minus 0. On the denominator it becomes 1 plus 0. If you look at it, it becomes limit x approaches positive infinity 2 over 1. And limit of a constant is a constant. So the answer is just 2. And the shortcut of this to solve this problem, you just, since x approaches infinity, right? So as you can see, negative 1 compared to 2x is nothing. On top, you just leave as 2x. On the bottom, again, 1 compared to x is nothing. So replace it, then you cancel x out. I'm going to limit x approaches infinity, which is just 2, right? Then it becomes 2. So you take the leading term on the numerator and take the leading term on the denominator and divide it. And also we find the limit. So this is kind of a shortcut, but just requires some analysis. Okay. So if you do direct substitution, you get a infinity over infinity, right? So to solve this, then we divide both numerator and denominator by x. Then you follow all these steps I just show you. Then you apply the theorem, becomes 2. Now y equals 2 is horizontal asymptote for this particular function. If you look at it, this is y equals 2. So the guideline for finding limits at the positive and negative infinity of rational functions. If the degree of the numerator is less than the degree of the denominator, then limit of the rational function is 0. It's very straightforward to demonstrate this. Let's say it could be plus minus infinity. Alright. So if you look at it, let's say numerator is x squared, denominator is x cubed. If you simplify that, then we get 1 over x. No matter you plug in positive infinity or negative infinity into the function 1 over x, it will become 0. Okay, it's like a quick demo of this particular guideline. Second guideline, if the degree of a numerator is equal to the degree of the denominator, then the limit of the rational function is the ratio of the leading coefficient. Another example could be limit x approaches plus minus infinity 2x cubed over 3x cubed. Right? Maybe plus 1, and just take get rid of the 1, because compared to infinity 1 is nothing, so we get a limit. So 2 over 3 is the answer, right? Just cancel x cubed and then become 2/3. That's what we mean by the limit of a rational function's ratio of the leading coefficient. The third one, if the degree of the numerator is greater than the degree of the denominator, then the limit of the rational function does not exist. In this case, you have x cubed over x squared. When divided, it becomes limit x approaches plus minus infinity x, then limit of infinity is infinity, so that means limit does not exist. Limit of the rational function does not exist. Okay. Let's take a look at example number 4, a function with two horizontal asymptotes. Okay. And let's say we have the function first one. It's the same function, f of x is equal to 3x minus 2 over square root 2x squared plus 1. And now we want to take a look at the horizontal asymptote, right? When x approaches positive infinity, then what we do is we divide the numerator by x. We also divide the denominator by x. And this becomes limit x approaches infinity. You divide the numerator, get 3. X get cancelled, minus 2 over x. So we take care of the numerator part. Denominator is going to turn into 2x squared plus 1 over square root of x squared. Right? Just after that you can just divide it. Since x is positive, so we get a limit x approaches infinity, and it becomes 3 over 2 minus 2 over 3 minus 2 over x, and this becomes radical of 2x squared over x squared is 2 plus 1 over x squared. And when x approaches infinity, plug in infinity, then limit x approaches infinity, 3 minus 2 over infinity. On the denominator we get a square root of 2 plus 1 over infinity square. It just becomes limit x approaches infinity, 3 over, the other one becomes 0, right? Radical 2 minus 0 plus 0. So it becomes limit x approaches infinity, 3 over radical 2. The result is 3 over radical 2. If you rationalize this, you need to multiply both top and bottom by radical 2. You get 3 radical 2 over 2. Okay. Okay, let's take a look at the second one. Let's find a limit when x approaches negative infinity. So again, we divide both top and bottom by x. So 3x minus 2 divided by x. On the denominator, we do the same thing. Square root of 2x squared plus 1 divided by x. In this case, since x is negative, so numerator stays as it is, no change. It's negative infinity, negative infinity. So we got 3 minus 2 over x. But on the denominator, when you because x is negative, in order to guarantee it's negative, so you gotta put a square root of 2x squared plus 1 over negative square root of x squared. Okay, because we're gonna guarantee, you end up with a negative number, right? Because x is negative. because after radical it's always gonna be positive, so that's why I put negative sign in front of it. Okay, then you divide it, you get a limit x approaches negative infinity. It's 3 minus 2 over x over radical of 2 negative plus 1 over x squared. Then plug in 0 and you end up with a limit. Plug in negative infinity for x, right? So 3 minus 2 over negative infinity over negative radical of 2 plus 1 over infinity square, negative infinity square. So they both become 0, so you get a limit when x approaches negative infinity is 3 over negative radical 2. So become negative 3 over radical 2, and the answer is negative 3 radical 2 over 2. In this case, left hand behavior, right hand behavior ends up with the opposite result. That's when a function with two horizontal asymptotes. Okay, it's the detailed demonstration. Yes, and then for x less than 0, this is a tricky part, right? X is equals to negative square root of x squared. Okay, and divide both the numerator and denominator by x. End up with that. That's exactly what we have. Here, this is a key thing, because anything after the square root become positive. So this part is always positive. Or we have to put a negative sign in front of it to guarantee it's a negative result, because x is negative. As you can see, when you graph the function, then two horizontal asymptotes, and one horizontal asymptote to the right, what's that? Horizontal asymptote to the left. So functions that are not rational may have different right and left horizontal asymptotes. And this is like, you can use it as an empirical rule. So this is the case with two horizontal asymptotes. And let's take a look at the infinite limits and the infinity. So definition of infinite limits and infinity, that f of x be a function defined on an interval a, comma positive infinity. The statement limit when x approaches positive infinity for function f of x equals to infinity, meaning that for each positive number m, there is a corresponding number n is greater than 0, such that f of x is greater than m whenever x is greater than m, capital letter M as Nancy. The statement limit when x approaches positive infinity for f of x equals negative infinity means that for each negative number m, there's a corresponding number n as Nancy which is greater than 0, such that f of x is less than m as Mary whenever x is greater than capital letter N as Nancy. Okay, let's take a look at this particular example really quick, right? Let's learn how to find infinite limits and infinity. So when limit approaches positive infinity for x cubed, and you get a plug in infinity here, right? We get an infinity to the third. Infinity to the third is still infinity. So limit when x approaches infinity is infinity. Okay, positive infinity. When x approaches negative infinity for x cubed, here when limit x approaches negative infinity, we get negative infinity to the third power, negative number raised to the third power, still remain negative. Still remain negative infinity. So negative limit of negative infinity is negative infinity. So that's basically what graph of f of x equals s cubed. As you can see, this is the graph. It goes up without bound and goes down without bound. So limit when x approaches positive infinity for f of x is positive infinity. Limit on the left hand behavior where x approaches negative infinity for f of x is negative infinity because it goes down without bound, right? Go up without bound. Okay.